Welcome back, and I've got another lovely experiment to show you today. What we're going to be looking at is Lenz's law. So the apparatus I've got here is really simple. I've just got a piece of very thick-walled copper pipe. It's like a plumbing pipe. And I've got two masses here. They're both the same mass. They're both the same weight, therefore. And they look to be identical. So what I'm going to do is I'm going to take this one and just drop it into the top of the tube and see what happens. Okay, so here goes. In it goes and straight out the other end. Sort of free fall, as it were. It's not a tight fit, so it falls through really easily. And I bet you're not at all surprised by that. But what I'm going to do now is do it with this other one I've got here. So let's repeat the experiment with this one here, which looks identical, and we'll just drop it in the top and go. Now, that's really rather strange. I wonder if you can explain what's going on here. So now for a bit of an explanation, and clearly these two objects are not identical. Everything I've told you so far is true. They're the same mass, so they have the same weight. Not that that would matter if you think about it. If one was lighter and one was heavier, as long as the air resistance wasn't too large, they would both fall together. But this one falls straight through very rapidly, and this one seems to take quite a while to go through, and this is nothing whatsoever to do with friction. So let's explain what's going on. This one here is just made of any piece of metal. Okay, it's perhaps a bit of steel or something like that, and it falls through under free fall. Now I'm in trouble because which is which? Let's try this one. Oh, right, first time. The other one takes quite a while to fall down through the system. And this one is magnetic. And the key to explaining this experiment is the fact that one of these is not magnetic and the other one is a very strong magnet. So to explain this, we're going to use Lenz's law. We've got our copper pipe here, and it's circular in its shape. Not that that matters too much, but we've got a large mass of copper and we've got a very strong permanent magnet. And if we drop the magnet in, it actually doesn't matter which way it goes through, whether I turn it around and put it through the other way. What we've got is a strong magnetic field cutting through this copper. Now this copper is a very good conductor. So if we have a changing magnetic field in it as the magnet goes down, we cut through the shape of the copper with the magnetic field due to the permanent magnet, and that magnetic field induces a voltage which then drives a current through the copper that conducts well, and that current creates its own magnetic field which opposes the magnetic field due to the object that we dropped in, the permanent magnet, and that is the key to understanding Lenz's law. So there we go. This one that isn't the magnet drops straight through because it doesn't have a magnetic field associated with it. It doesn't therefore have a magnetic field that cuts through the copper pipe, induces a voltage, drives a current, which creates a magnetic field, which then opposes the magnet falling. This one does. So this one does have a magnetic field associated with it, will induce a voltage in the copper pipe, will create a current, and the magnetic field due to that current will oppose the motion here. In other words, it has the effect of stopping it from accelerating down the pipe. Now, if you think about it, one of the keys to Lenz's law is that the cutting of the magnetic field through the copper pipe has to create another magnetic field that opposes what that's doing. Otherwise, what would happen is you drop this in and it would get faster and faster and faster and faster, and it would be gaining energy from somewhere. And that's not the case. It's really nice, in fact. It falls through the copper pipe, about at a constant velocity. And I'll show you how we can see that happening with this pipe. Now, without getting really complicated, some teachers get in a bit of a tangle with this one because they say you have to have a continuous loop. Do you remember I said you need a mass of copper? You don't actually need a continuous loop. And this pipe has got a slot machined into it with a clear window in it. So when I drop the magnet in, you can actually see it passing down the tube. But there's enough copper here to create eddy currents in the copper that will create magnetic fields that will oppose the magnetic field due to this one. Just before I finish, you can probably make one of these at home. The thickest plumbing pipe that you can find, and then you need some really strong magnets. And what we've done in the lab before now is bought little tiny circular section magnets and stacked a few on top of each other. And if you drop them in, it will work quite nicely. So I hope you enjoyed that video on Lenz's law and you feel you've got a better understanding of it now. I'll be making another video soon, and I look forward to seeing you then.